Welcome back. Today we continue with our work on the Callan-Symanzik equation. Right? Last video we obtained the beta and the gamma function for a number of theories, especially lambda phi 4 and QED, our two favorite ones. And today we move towards getting an explicit solution to the Callan-Symanzik equation. Right? As we know, the Callan-Symanzik equation is an equation for green functions, and we start with the simplest one we can think of, which is G2. Right? The first important fact we can use when solving for G2 is the fact that in the massless case, which is the one we're looking at so far, right? You can think of the massless case as the ultra-relativistic limit of these theories, when I can forget the masses of all the particles, right? In that limit, we have very few mass scales, right? We have for certain the external momenta, right? In the case of G2, just one momentum, right? And of course, we have these artificial or not physical scales, right? The renormalization scale being the one we choose, right, to keep in the theory, right? And in that case, some dimensional analysis can help us rewrite the Callan-Symanzik equation in very interesting ways. Right? So the first thing to remember is that the dimension of the two-point green function is the same as the dimension of the free propagator of the theory, which is the very first contribution to that function, right? And that's -2 in terms of natural units, right? GeV to the -2, right? And that means that in general, right, in the ultra-relativistic limit, I can write this guy explicitly, right, without any laws of generality, as something that is a function of 1 over the external momentum, right? This choice is made with this I up here to match the free theory propagator in some limit, right? Times a function which can be pretty complicated. I'm calling this function G, right? But which is for sure a function of p squared over m squared, and this minus is just convention, right? So all the dimension is contained here, right? So this function must be dimensionless, and the dimension of p squared, the dependency on p squared inside this function, must be compensated by the only other scale in my theory, which is this mass square. So keep in mind that the dimension of this function g is 0. And that will be useful in a few moments. We'll see how. Right? Another thing that I want to make explicit is the fact that we're limiting ourselves to the Euclidean region because we want to avoid complications in this other region where you have possible on-shell intermediate states, right? So in order to make that very, very explicit, we'll be defining this K momentum here, which is by definition the positive square root of minus p squared, right? And that guy is explicitly just a number, right? This is not a 4 momentum, right? It's just the module of this guy, right? And is by definition positive, and that's what we're talking about. So I want to rewrite the green function in this way. Times g of k squared over m squared, right? And that's the general form we are assuming for G2, right? But that's pretty general in the ultra-relativistic, the massless limit for these theories. Now, we can see that if this is the most general form of G2, we can make some substitution on the partial derivatives that show up in the Callan-Symanzik equation, right? And in order to do that, let me quickly define another variable, right? This x which is defined as k over m. So g is a function of f, x, right? Of these x here, right? And then we can now rewrite a few of the partial derivatives, right? There's two that I'm especially interested on, right? Which is the partial derivative in the renormalization constant of any function that depends only on x, and that's the main point, right? This function cannot depend on k or m separately, but only on this ratio, right? And I want to compare that partial derivative with the one in k. This one I can rewrite as this dx dm df of x dx, right? And this is, of course, I just have to take dx dm here, right? This is k over m squared df of x dx, right? These are all partial derivatives here, right? And that allows me to, on the flip side, right, invert this relation and write this as df dx is equal to minus m squared over k del f del m, right? By the same token, I can do the same thing here, right? This will be dx del k del f of x del x, which now is just 1 over m, right? I just have to differentiate here. Del f del x of x, right? Which now I can invert, right? And rewrite this as del f del x equal m del f del k. Right? And now I can equate these two expressions, right? I can put them together and get what I wanted, which is that the derivative in m is the same as minus k over m, the derivative in k. And that's what we want to use, right? Because now I can go back to the Callan-Symanzik equation with this and replace derivatives in this unphysical renormalization constant by differentiation in relation to the physical momentum, right? This is the physical momentum. Huh? So let's take a look how can we do that, right? So I can start with this expression. Remember, this is one of the terms that shows up in the equation, in the Callan-Symanzik equation, right? Is g del m of g times m, right? Now I want to use this generic expression for g, specifically this one, right? These I can write as minus m I over k squared del m of g, right? Which is a function of k squared over m squared, right? And I can use now this relation, right? I can exchange the derivatives, right? So this m cancels with this one. So I have minus I k squared out here, minus k del k acting on g, right? Now, this derivative acting on little g is not very useful for us. I want this derivative acting on the whole green function, right? In order to put that explicitly in that way, we can do a little trick here. First, I exchange these two parts, right? Because this is very similar to the propagator. I bring this k outside, and then I just have to remember that I want this derivative acting on g2, which is, right, something like this. This is the whole g2, right? And this, if I just do the derivative, right, this is 2I over k to the cubed, right, times g minus I k squared del k of g. This is exactly what I have here, right, inside this parentheses, right? So I can use that fact, right, to rewrite this expression. Right? Let's bring the minus k over here, right? And now I just have to isolate this on the other side, and I'll have these two pieces right here. So the first one is just this. Let me turn that to white. Minus this part. So minus 2I k cubed g. Which now I identify g, capital G, to here. And in here I have 2 over k times capital G. Right? So in conclusion, I have minus k here, del G to del k, plus 2 over k G2, right? Which I can do a little bit of simplification here. There's this minus here, so I can bring the, let me bring the G2 to the right, erase it from here. This minus k goes in here and cancels this one. And that's what I wanted, right? Oh, there's an extra minus here. Let's not forget, there's a minus, it goes in there, right? This was 2 over k, so there's another minus. Yeah? So in summary, right, we can now rewrite, remember from last video, we got the Callan-Symanzik equation for the 2-point green function in this way, right? For a one coupling theory, in this case I'm calling the coupling lambda, right? So there's a del lambda here plus 2 gamma of lambda G2 is equal to 0, right? So this was the Callan-Symanzik equation, and now I can use this part, right? This equation here and rewrite this as this one. It's the same equation written in terms of different variables, right? Plus 2 minus beta. I compensated for this sign, right, on these two terms. Minus beta del lambda minus 2 gamma G2, right? And this is pretty important, right? It seems like a trivial change, right? But it is one with a lot of physical significance, right? Because as I have, warned before, right? The fact that on the high energy limit, on the ultra-relativistic limit, these renormalization constants always, the normalization scale here, always comes together with the external momentum, right? Compensating for the dimension of one another, right? That meant that if I found the dependency of my couplings and my green functions in terms of these renormalization constants, I would also gain their behavior in terms of the external momentum, which is actually the physical thing we see, right? This very trivial thing we just did which depends only on the fact that these guys depends on these ratios between the physical momentum and this unphysical renormalization scale, right, allowed us to rewrite now the Callan-Symanzik equation in terms of the external momentum, right? You see, it's a very trivial step, right? But depends on this very important thing, that how the dimensionful scales behave in our theories, right? In fact, this equation now has at least one very trivial solution, right, which matches our free theory, right? If I think on a free theory, right, we have no beta function, no gamma function, because there's no loops, and you might recall that these guys show up at some power in the coupling constant. So if I take all the coupling constants to zero, they go to zero, right? And in that case, this equation is just k del k of G2 is equal to minus 2G2, right? Which now admits as a solution G2 is equal to minus I k squared, which is exactly the free propagator in a massless scalar field theory, right? So you see, now we're moving towards solutions to this equation. Of course, this one is too trivial, right? But you can see that at least it's a very most basic check of this equation right here. Now, in order to solve this equation in more general cases, right, let's use a very funny analogy, right, due to Coleman, and also used in Peskin and Schroeder's book, which is considering some combination of biology and hydrodynamics, right? So we'll think now of a system that consists of a unidimensional flow of some kind of live thing, some bacteria, you name it, right, flowing through a one-dimensional tube, right? So the thickness of the passage here plays no role, right? The only thing is where, since you have a constant flow of liquid here carrying some bacteria, let's say, right, it flows quicker where the tube is narrow, right, and slower where the tube is more wide. So you have really a speed for this velocity for the movement of this liquid, which is dependent on this position x, right? And also you have some conditions for the proliferation of these bacteria, which say depend on something, right? Some function rho, right? Rho of x. Let's say which represents the lighting, for instance. Say some bacteria that feeds on some plants that reproduce more where there's more lighting and less where there's less lighting. So the more lighting, the better. And this is the function that tells me how good the lighting is for the bacteria in that particular spot. And we want to describe some density function. So there is a function that depends on the position and time, right? And this is what describes the density of bacteria at any position on this tube, right? And now we want to write a differential equation for this function. So I want to know how this function changes as time passes, right? So I want to know this quantity, right? There's two terms for that in our model, little model here. First is what I call the population drag, right? So there's a term which is proportional to this velocity, right? And to whatever the density, if you look at any particular position here, this is sensitive to what the density of bacteria was to the left, because this is being dragged to the right. They are dragged with the liquid, right? And so this is dependent on the gradient of bacteria through the liquid here, right? And so let's write this term. If you're worrying about the sign here, just remember that, say, if the derivative in position, let's first think the case where this is a positive, right? Dx is positive. That means the curve is something like that, right? At that position. And as it gets dragged, right, you go from a time t equals 0 here to another one as the whole distribution gets dragged by the flow of the liquid to the right, you get to another distribution, which means that in that fixed position, right, you saw the density going down, right? So there's some variation in density here, which is negative, right? So if this is positive, the variation with time should be negative, and that's why you have this minus sign here. V here is just the module of the velocity, right? So you should have a minus sign here. Of course, the situation is exactly the opposite. If the derivative is negative, these curves would be going down, and as you move, the density goes up, right? So this is the first term we're interested in, right? This population drag. And of course, there's another one that is just what living things do, which is reproduce, right? And that is influenced by this rho here, which tells me how favorable the conditions are here. So there's a condition that changes along the x axis, right? But then, of course, the growth is proportional to the density itself. The more bacteria you have there, the more fun they have and the more they grow, right? And of course, this is all very construed, right, to be very close to the equation we want to solve. So let me copy it here, right? So what we want is an equation which is really analogous to this one. And you see that it is, right? I have a derivative in x, which will be equivalent to this derivative in lambda. The derivative in time will be equivalent to derivative in k, right? I have a dictionary. If I want to go from one equation to the other, let me explicitly write this. Since I have k, the delta k here, and here I just have the time derivative. This is a log derivative, right? So log of k over m will be mapped on t, right? And if you're confused about this, just remember that dt is mapped into 1 over k dk, right? And that means del t is k del k because of this relation, right? Just take the derivatives on both sides here, and then you get here, and that's k del k over there, right? Lambda will be mapped into x, right? This is the easiest part, right? Beta, the beta function of lambda represents this velocity of the drag there, right? Except they have opposite signs, right? You see, if I throw this to the left side, everything will be, this guy will be positive, this one will be negative, right? 2 gamma minus 2 is rho of x, right? Just take rho to the other side. You see rho is negative, so I have 2 gamma minus 2, right? And of course, g, the green function, that depends on k and lambda, right, is my density, right? So this is maybe a very strange map, but it's just a trick, right? Because we have more intuition solving this equation than directly this one. And once we get the results, we can use this map to find the answer to this one and test if we had any mistake along the way, right? You can, once you know the answer to a differential equation, it's very easy to test if that is the true answer, right? So now, let's think of the bacteria first, right? Suppose we have some initial condition, and we know at some time equals 0, we know the full distribution. For every point, we know how this population distribution starts, and I'll call this di, and this is just initial, right? And this is just a function of position along that tube, right? That part is clear. Of course, if I want, suppose I look any point here, say a point that I call x1, at some time t1, which is bigger than 0, right? T1 bigger than 0. I'm looking here at a particular point in time and space. Right? And I want to know the density here. Of course, this will depend on the whole story of some element here of this population, right? As it goes through, right, it has spent more or less time in each part of the tube, right, and faced easier, right, or harder conditions in each part. So I have to kind of integrate through this whole past story, right, history of this density element here, of this particular part of the population, right? In order to do that, it's useful to define this small interval, right? This small element as moving towards the past in time, right? I can define something which I'll call x bar, which is the position of this guy, right? If I go a certain time towards the past, right? So this guy is actually moving with this other time variable, which I'm calling t prime, right? And this is a function of t prime x1, right? This is just a reference point. It's not, this is a position. It's not depending on x1, right? And this guy is moving with a negative velocity. So it's moving towards the left as I increase t prime, right? And this index x1 here only means that when I take t prime equals 0, this guy is in x1. And as I increase t prime, I looking more and more towards the past, right? Until I get to x bar t1 x1, right? So I took the same amount of time to go back to my initial conditions, right? And this is the position, right, of this particular element here, right, at t equals 0, the time where I define this, right? So to make things clear, I have my usual time, right, which with which my density is evolving, and my initial conditions are set at t equals 0, and I want to know them at t1, t equal to t1, right? And this new variable t prime is the opposite, right? At t equals 0, t prime is t1, right? And at t equal t1, t prime is 0. And that's tells me how this thing propagates towards the past, right? So if I do a plot, just to make it even clearer, and I write this guy, right, which is an x bar of t prime comma dot x1, right? This guy starts at x1 point here, right, and finishes at some position x bar of t1 x1, right, at a time t1. So this is at t0, t equals 0, right, and it finishes here. And it does its thing depending on the velocity, which is not constant, right, along the tube. It's never negative, so should be univocals, right, like that. Now, so the initial density, right, as we have set the initial conditions for this guy, for the whole system in this way, right, for this particular element, at the start, at t equals 0, it was somewhere back here, right? So this guy was somewhere over here. This is x bar of t1 x1, right? This is where it was at the start. So the initial density of this particular element is, right, di of x bar of t1 x1, right? So this is just a number, is the position when I knew the whole density, right, at t equals 0, not t prime equals 0. Now, if I sit on the reference frame of this particular element of the population, right, just sitting on this box, right, on the reference frame of this box, then there is no population drag, right, and my differential equation is just vegetative growth, right? It's just a growth proportional to the population itself times some constant, right, at that position, right? So this thing will only change now if I'm sitting at on top of this, because this is moving, so I'll see this as a dependence on time. Rho will actually be dependent on time because I'm sitting there and I'm seeing the illumination change. That's how the bacteria feel this, right? So in this case, we know the solution, right? This is an equation that looks like that, del t dt of rho t dt, right? This is just exponential growth, right? As we know, especially post-pandemic, we know how that goes. This is just exponential. And since this is not really a constant, right, I have to integrate for the conditions in this whole time interval, right? So now I can think this in terms of the t prime, because it doesn't matter if I look the package moving to the past or moving to the future, right? I can just consider the equation in the right time direction, right? But it grows in each point locally as if according to how favorable the conditions are, right? And that means that I can write the general solution for t1 x1 now as the initial condition, right? Which we have already seen, that is di x bar t1 x1, right, times the exponential of this, right? 0 to t1 dt prime rho of x bar t prime comma dot x1. Let me write it in this way, right? So see, now I'm integrating in time, right? But the position, this position is moving as I increase time, it's moving towards the past and passing through all of these conditions row at the right position for each case, right? We can also use the fact that t prime and x bar are related by this equation here, right? And if we want, we can write the same equation in this way, so we can use the dt prime is equal to minus 1 over v of, let's call this x bar prime, because it will become an integration variable, right? So that's why I'm putting the prime, the x bar prime, right? And then the conditions are that t prime equals 0 means x bar prime is equal to x1, and t prime equal t1 is equivalent to x bar prime equal x bar of x1 t1, right? Which are both just the conditions in this plot, right? T prime 0 x1, t1 x bar, right? And then I can rewrite this integral if I want, right? Both of these equations, this is already the solution, right? But both of them can be useful. I can write these in terms of the time integral, but I can also write in terms of the position integral. This is just repeated, right? Times the exponent, times the exponential of the integral from x bar of t1 x1 x1 the x bar prime. You see why I'm putting the prime, because there's x bar here and x bar there, right? And this is just rho of x bar now, which is prime because it's my integration variable, over v of x bar prime, right? So let me copy these solutions, because I can even simplify the notation a little bit. I have this one and this one, they are equivalent, right? And of course, I call this x1 t1, just I choose a particular point over here, right? But of course, that's valid for any value of x1 and t1, so I can drop. I just wanted to avoid confusion between x and x1 and x bar, you know. But now I can remove these 1 indexes, right? And just write this general solution in this way, right? Just drop this from here, here, let me see, here, 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 in all of those places, right? And that's the solution for my bacterial equation, right? Now let's go back to the less infectious world of quantum field theory and write these in terms of the field variables using our dictionary, the same one we have shown before. So the initial condition at t equals 0 now is equivalent to k equal m, right? So when my external moment is at this renormalization scale, t is 0, right? And that means my initial condition, di of x, which was defined as the density of the bacteria at time equals 0 and position x, now maps into the 2-point green function at momentum m and coupling lambda, right? This is the map between these two things. And now define a function, which I don't know right now, which is this sort of equivalent to the initial condition for the bacterial density. And I'll call this g hat to initial, right? The main point is this I here. The hat will be explaining pretty soon why I want that hat there. Right? but that's the equivalent of my initial condition here, right? And that's why I'm substituting the momentum for the renormalization scale. This is what our map says. Then I can rewrite this particular solution up here. I want to use this version with the time integral and write it using this dictionary. So G2 of K lambda is equal. So you have the initial condition here, Gi hat 2, right? But calculated at x bar, right? And so this is lambda, I'll call that lambda bar, and we'll see what kind of function is that in a second, right? K, this was a comma dot here, comma dot lambda, right? Remember that this guy was initially defined in this way. So this is just tells me where this small element of the population started, right? Started at position X when I remove the ones. And this is the same thing, right? In some way, this will be a moving coupling that starts at position lambda, same as this, right? And then there's this exponential, which can be a very complicated thing. It goes from, it's an integral, so dt prime will become d of log of some k, let me call that k prime, because it's not the same k here, it's just a variable of integration, over m. And it goes from 0, which is this condition, so k starts at m, and goes to some value k, which is this one, right? Same as here, right? So this is a density, I forgot to copy, but it was something like tx, right? So this variable t is the upper limit of this integral. And then there's rho, which is given by 2 gamma minus 2, again calculated at position x bar. So now I have 2 gamma of lambda bar k prime comma dot lambda semicolon, right? Comma dot is not I don't think that's the right way of saying it, but so semicolon lambda minus 2, and then close the exponential right here, right? Yeah, so that's the translation of this solution, and supposed to be already an explicit solution to the Callan-Symanzik equation. Of course, I have to also write an equation for lambda bar, which I'll do in a moment. Before I do that, there's a small trick we can do here, because that integral can be complicated. We need to know lambda bar, plug that in, then use the expression we have to for the gamma function, and then calculate the integral. But there's a small part here, which is this minus 2, which is just the integration of the log of a constant, right? This will be the exponential of minus 2, which is right here, integral from m to k of the log, right? K prime over m, which is easy. This one is easy, right? This is just the log calculated at both extremes. The lower limit is just 0, right? The upper limit is just the log of k. But then I have this minus 2, which I can exponentiate and make this the log of k squared over m squared, and take the exponential, right? Just take the exponential. So this is just m squared over k squared. And this inversion is this minus here, because I can take this minus 2 and then invert. Instead of having k over m, I'll have m over k squared. Right? So this one I can group with this guy, right? I can bring this part of the integral up front and define m squared k squared times this g hat I 2, right? And I can define this as minus I over k squared g I 2, right? That means this function has not the same dimensions as this one, right? But on the flip side, I have this explicit form for J2, which makes everything from this point on, right, dependent only on the ratio between k squared over m squared, because at the start we have seen that G2 is something like I over k squared times g of k squared over m squared, right? So writing it in this way, I can have that explicitly, right? And that's what I want. So using that trick, that's why I had the hat at the start, right? I'm explicitly defining a second initial condition, which is different than this one by some constants, right? I just multiply by I m squared or something like that, right? So now I can rewrite this in the way I wanted, which is my solution to the Callan-Symanzik equation. Okay, formal solution. Still have to find lambda bar for that to be of any use. Now I have minus I k squared g I 2 of lambda bar k semicolon lambda times the exponential of everything here, except this minus 2, which I integrated already, right? So that's it. Let me just close all the parentheses here. I can bring these 2 to the front. And that's where I close the exponentiation, right here. Now, of course, in order to use that solution, I also need to know who this lambda bar is, right? I have to solve for this, going back to the bacteria, this element of population. I have to solve for the whole history of this element of the population. As you might remember, right, the equation for x bar was that del t of x bar t x1 is minus v of x bar, right? And that I can translate now using the same dictionary, right, to an equation for lambda bar, which is a very important one. So time translates as the log of k over m. Lambda bar of k lambda is equal, the minus v is just beta, the beta function of lambda bar k lambda. With the initial condition, remember for this guy, the initial condition was that x bar of 0, x1 was x1, right? So that translates to lambda bar. Remember, time 0 means momentum equal to the renormalization scale. Lambda is equal to lambda, right? So that's now also a differential equation for lambda. In fact, this is another renormalization group equation, right? This is the renormalization group equation for the coupling constant, right? We'll see that this lambda bar is the effective coupling constant, and that's the initial condition, right? These two together, if I know the beta function, and that we have already calculated for a few theories, right? Then I can solve these to get lambda bar, right? And notice what is happening here, right? So that's very important now, because it allows us to reinterpret or to interpret these lambda bar in very familiar terms, right? So this bacteria analog, right? We had this packet, right? And this X bar gave me the position, how the position of this element of population changed as I changed time, knowing that it started at some reference position x1. And lambda is the same, right? This is how the coupling changes, right? As I change the external momenta, right, is starting at a reference point m where the coupling constant is a constant, right? It's just a number lambda, right? That's my reference point. That's the value of lambda bar at momentum m, right? So this is the running coupling constant, now written in terms of the external momentum and some reference coupling, which is the same we did for the running coupling constant before, right? Now we can solve for lambda, but we also need to find out this function right here, right? We need these initial conditions. By the way, even before you figure out who GI is and the explicit expression for lambda bar, you can already show that this solution is a solution to the Callan-Symanzik equation. You just have to use these properties of lambda bar, and even easier to use this version with the g hat and the -2 here, right? Plugging these straight away into the Callan-Symanzik equation and showing that you get a solution. Right? I will leave that as an exercise. Right? In order to find this guy, what I can do is do the perturbative expansion on both sides of this equation. Right? So if I take on the left-hand side G2 calculated at this point K equal m, right? Then you see that, and do the perturbative expansion. So I just take what I know for the green function, right? This is a propagator, right? So in leading order in perturbation theory should be just 1 over p squared, right? In this case, m squared, because I'm taking k equal to m, right? And of course, there are corrections of order lambda square, as we have seen in lambda phi 4 theory, right? And then I can compare with this, right? If I take k equal to m on this equation, right? This will be minus I over m squared, is the same thing, right? Then I have gi 2 calculated at k equal to m, right? But if I take lambda bar of m lambda, this is just lambda, right? Let me write it like that, m lambda. And this exponential, right? I'll just take m equal to k equal to m, so the integral is just over a zero length, right? And this is just gives me 1. It's the exponential of 0, right? So that's just it, right? And of course there are corrections of higher order, but I can already solve here for G2, right? So GI2 of lambda, in fact, that's better like that, because lambda bar is lambda, there's no m dependence there. GI of lambda is just 1 plus something of order lambda squared. And since this is the functional form of this function, and I could have done that for any value of m and lambda, right? I can just change that continuously, and we have seen that before, right? there's implicit dependence between these two guys, right? I can write now the general expression, which is that GI2 of lambda bar is equal to 1 plus something of order lambda bar square, right? This is not very enlightening, right? You're just seeing that the initial condition for this function, right, initial as in k equal m condition, is just the free theory, right? Because if I put 1 here, I just get the free theory. But I can do that also for higher higher number of external legs, green functions, right? Higher order green functions. So take G4, for instance. Now G4 depends on 4 momenta, which I can call P1, P2, P3, P4, right? I don't want to study 4 independent variables of momentum, so I can simplify that by choosing a specific kinematical region, right, in which all pi square are equal to some, let's call this capital P square, and this guy is bigger than 0, and that all these guys are orthogonal, say pi and pj equals 0, whatever I and j, which are different, right? Whatever different I and j. That's equivalent to taking all these Mandelstam variables equal to the same scale, right? So this is my the momentum going through this green function, right? And I'm saying, well, let's assume they are all the same. So now in this case, I have only p square, which is a relevant physical quantity, right? Everything else is unphysical. And G4 can be written, right, G4, which is now a function just of this capital P, right? And again, I can do dimensional analysis and see that this guy, the dimension of a green function with 4 external scalar legs, right, is the same dimension of 1 over p square to the 4th, right? So this is dimension -8, right? And then you can do the same as we did in the 2-point function, which is then this thing can be multiplied by an arbitrary function there, but which depends only on the ratio between this capital P and the renormalization constant, just because these two dimensions need to compensate, right, in order to give dimension 8 for the whole thing. That means now we can do the same thing we did before. I can do this exchange of the derivatives in the renormalization scale for derivatives in the external momentum, right, momenta, and rewrite the Callan-Symanzik equation. The only real difference is now this dimension, which is 8, before was 2, right? And that means now when I exchange these for that, right, instead of a gamma -2, I'll have a gamma -8, right? Can do it all again, but it's pretty trivial. Now my Callan-Symanzik equation will look like this. Let me write every term. So that's the coupling part. That's the 8 coming from the dimension. And this is the number of external legs times the gamma function. Right? Before we had a 2 here because the dimension was 2. So that's it. Right? And my 4-point green function should satisfy this equation, right? Analogously, right, I just use again the bacteria example. I'm just changing the mapping, right? So this term is my, in the the bacteria map, this was rho, right? The conditions at each point in the tube, right? But the velocity is the same, the derivatives in P are doing the same as the derivatives in K, so not much is changing here, right? And I can write my general solution. I won't do everything again, but G4 is a function of P and lambda, which will be given by I over P squared to the fourth. This comes from the integral of this 8, the exponential of the log that will be multiplied by this factor, right? That removes the hat from GI here. Same story as before, right? You have lambda bar of capital P semicolon lambda, right? Times the exponential of 4m capital P d log of k prime over m gamma of lambda bar, which itself is a function of p prime lambda, and that's it, right? So that's the solution for the Callan-Symanzik equation for the 4-point green function now. And you see it's pretty easy to go to higher point green functions because the tricks are all the same. You just change a little bit the mapping here and the integral, the factor that will come out in front here, which is pretty obvious, which is the natural way of doing it, right? So now if I want to figure out this guy, right, this initial condition for the 4-point function, I do the same I did in the case of the 2-point function, right? So this 4-point function, we know from perturbation theory that at leading order in perturbation theory, this is just the Feynman rule for the theory, right? This is just the leading contribution, is just this diagram, right? Which is minus I lambda for the vertex here, times 4 propagators, which in a massless theory is just this, plus order lambda squared. So this is my initial condition, it's just the 3-level theory, right? The running is generated by the loops, right? So my initial situation is no loops, and then I'll see how the loops change the theory. Right? If I do the same on the right side of this equation, I get just now the same thing, but coming from this calculation. This is just what we knew from perturbation theory. Now here I just get I p squared the fourth, right? G I to the fourth, GI4, right? And I'm calculating this. I want to calculate this at P equal M, right? That's the whole point on both sides of the equation, right? So on this side, I take P equal M, and then this integral goes away. I'm left only with GI calculated at lambda. And then I just have to compare these equations plus whatever. I just have to compare these two, right? And get that GI for calculated at lambda is minus I lambda plus higher orders, right? Which means, again, since I can change lambda and m at all points, right? This is the functional form of this guy. So it needs to be EI 4 of lambda bar is equal to minus I lambda bar plus order lambda bar square. So that's the form of this function for the 4-point function. Now we can see what the Callan-Symanzik equation is doing for us, right? We already know from our previous renormalization studies, right, that in any case, a green function in lambda phi 4 will depend on two things, right? At one loop, say. It will depend on the coupling constant, but there were also these pesky logarithms that grew as I moved away from these unphysical and arbitrary renormalization scale, right? And then we saw that there might be a problem, right? Even if you're in perturbative region, if you move too far away from this scale, which is not even physical at all. Now, the Callan-Symanzik equation has reorganized these, right? It has reorganized in the way that now, you see, my green function is directly proportional to some lambda bar, right? Which changes as I change the scale, and to some exponential, which is also multiplying this coupling, right? And it's multiplying this initial green function, which is valid at p arbitrarily close to m, right? And giving me the field renormalization part of the running, right? You see, remember the gamma function is the part that controls the field renormalization. I'm multiplying by the number of external legs here, right? So this is equivalent to z to the power half to the fourth, right? This is this part here. And the other part is really how the coupling changes, right? This is more explicit than anywhere else in the 4-point function right here, because my G4 will be proportional to 4 propagators times the z's, right, that are coming from here, and the coupling, but now the coupling is not lambda, is lambda bar, which is one of the things that we wanted, right? It would be really nice if we could do an expansion now in powers of lambda bar instead of powers of lambda, right? Because that incorporates already the big logs in here, and I don't have to worry about two separate things anymore, but just the value of this lambda bar, right? Which is a more appropriate expansion for my perturbative series, and it is this running coupling, this effective coupling, whatever you want to call it, right? To see this more explicitly, right? Let's see the explicit solution for lambda bar in lambda phi 4. Right? So we have calculated, and this is pretty neat, we have calculated the beta function for lambda phi 4, and this is just 3 lambda square over 4 pi squared. This is on the last video or the one before that, right? Plus things of order lambda cubed, right? Now I want to know what lambda bar of k lambda is, right? In order to do that, we just have to solve this particular equation, which is the equation for lambda bar k over m lambda bar equal to beta of lambda bar, right? This equation is now, since I know beta, this one, 3 lambda bar square over 4 pi square, at this order, right? I don't have to write this anymore, right? And the initial condition, as we have seen before, is just that scale m lambda bar is the same as lambda. Now this equation can be solved by separation. Here I can take d lambda bar over multiplied by 1 over lambda bar squared. Just bring this to the side, send the log to the other side. This is 3 over 4 pi square d log, right? And I integrate on both sides. This is just minus 1 over lambda bar plus some integration constant. It's equal to 3 over 4 pi square log of k over m, right? And these, of course, together with this one, set the integration constant, right, to 1 over lambda. Just have to substitute m here, right? This will become 0, and then c is equal to lambda, because lambda bar is a lambda bar of m. When I put m here, I get rid of the bar, right? So the general solution is this. Which now I can reorganize to get lambda bar of k lambda. Just have to put this guy on the other side, invert, and I get lambda over 1 minus 3 lambda over 4 pi square log of k over m, right? Which you might recognize as something very similar to the effective coupling we got before for QED, right? I don't think we did lambda the effective coupling of lambda phi 4 on any of the videos before, but now we got it, right? And it's very similar to what we saw in QED, right? You have this structure, which is the coupling, this constant, right? Remember, this lambda here is not really the coupling anymore. We have been looking at these through various perspectives, right? For one, these might be very similar to the running of the Wilsonian approach, right? We'll compare this with the Wilsonian approach pretty soon. But also in this case, you can see that lambda bar is what really controls the 4-point green function, right? If I move away from k equal m, right? And the same thing is showing up here, right? If I take k equal m, lambda bar and lambda are the same, but that defines at the same time m and lambda. This is a pair that gets defined together, right? And then as you move away from that point, you get a running complete constant, right? And this shows us how it runs with the physical momentum, right? And now if we expand, right, we have talked about this in the context of QED, right? In the context of QED, we have seen to get to something like that, we did resummation, right? This is exactly the same expression, the kind of expression that you get at the leading log approximation for QED, right? Or for lambda phi 4. But now we didn't really resum any 1pi contribution. Remember, we actually worry about that in the previous video, that I was doing a resum like that, right? Which includes higher order of the couplings here, right? But I was not putting two loop contributions, which in principle have the same coupling. And that was okay as long as this sum gave me something like alpha times alpha, in this case lambda, right? This is QED, but okay, let me write in terms of alpha, but alpha times the sum of alpha log, right? And this other sum that includes both terms like that and terms like this, right, gave me a sum of the form alpha square sum of alpha log to the n, then this approximation was okay. But I had no guarantees just looking at this that I didn't have the wrong powers of alpha, right, to sum here. Now, the renormalization group equations are already giving me this resummed expression without any of these ambiguities, right? If I expand these uh, for small lambda times log, right, I can rewrite this lambda bar here of k lambda. I can rewrite this thing in this way, right? Here I'm just expanding this perturbatively. For plus order lambda cubed, right? And if I had, say, included two loop effects in my theory, they would show up here in the beta function, right? There will be this order lambda cubed or even order lambda 4 correction here that changes the solution to my differential equation, but it would show up here, so already in a resummed way, which shows me that stopping at loop expansion is better than stopping in the coupling approximation. Right? I'm taking all the one loop effects here, but now I could take all the two loop effects straight away into the beta function and solve a new differential equation, which would already have resummed all the two loop effects, right? The whole series at next to leading log approximation. You see? So now it's clear that we have the right powers, right? If we go forward in these series, right, you would get some structure that looks like lambda square log plus c square lambda cubed log square and so on, right? So the whole leading log approximation is appearing here, and you could go to two loop easily. Another thing that you can see here is that if I take this momentum here and I say I'm moving my external momenta away from this reference, but I do it by a constant. I just take b smaller than 1 m, right, and substitute here. Then this equation becomes lambda. I would just invert, right? This will be log of b, but I want to write in terms of log of 1 over b, so I take this sign outside. Which is exactly the running we found for the Wilson, also at this order, right? For the Wilson coefficient for lambda phi 4. So you see, it's the same thing again, just in a new language, right? This lambda bar is really the Wilson coefficient for the phi 4 operator, right? It's running just like it in terms of the same variables if I do this substitution. So you see that now we're basically closing a big logical loop and seeing that once we know how to solve these renormalization group equations, right? We are doing the same we did for the Wilson approach to renormalization, to think in terms of these coefficients that run, right? And we are getting the same effective couplings we did when we did counter term renormalization, trying to write some effective coupling that you see at arbitrary external momenta, right? It's all the same, but in terms of having a very not only straightforward but also um, theoretically clear way of doing it, the renormalization group equations are much better than the other methods, right? Because already it's clear what kind of approximation you're making. There's no ambiguities in terms of how you are resumming all those diagrams, right? You straight away get this guy, which is now clearly the proper expansion parameter for these theories, right? All I have to look at is at this guy and keep track of how it changes as I change the momenta. If this guy starts to get too big, then I have to stop. I don't know how the theory behaves beyond that point, at least not from the perturbative point of view, right? Then I have to calculate everything, including the beta function, the solution to these equations non-perturbatively, and that demands a whole other set of tools, right? But we can now delineate a region around this Gaussian fixed point, and that if all my running couplings are within that region, I know that perturbative expansion is working, because this guy includes both the effects of the big logs, the logs that can get big, and the coupling itself, right? And in one object, which is the real interaction, right? The real coupling for this theory. So this is the memo for the day. The next video we'll take a look also and this application of these ideas to QED. See you then.